In this video, we're going to review chapters 2 and 4 for the final exam. So if you remember, chapter 2 was about functions and chapter 4 was about exponentials and logarithms. So we're going to start with the following problem. So we have a function, f of z is equal to 5 minus 3z squared, and we want to determine the net change between the given values of the variable. So we have z is equal to negative 2 and z is equal to 0. So if you remember, net change is equal to f of b minus f of a. And a and b are the two values that we've been given. So b is always the bigger number and a is always the smaller number. So in our case, out of 0 and negative 2, 0 is bigger, so we'll call that b, and negative 2 is smaller, so we'll call that a. So now we just need to complete the formula. So if we want to find f of b, we want to find f of 0, which is 5 minus 3 times 0 squared, which is 5 minus 0, which is just 5. We also want to find f of negative 2, which is 5 minus 3 times negative 2 squared, which is 5 minus 3 times 4, which is 5 minus 12, which is negative 7. So now we want to take our values of f of a and f of b and plug them into our net change formula. So f of b was 5, f of a was negative 7. So we'll have 5 minus negative 7, which is just 5 plus 7, which gives us 12. So 12 is the net change. Next, we want to determine the average rate of change between the given values of the variable. So average rate of change, you can think of kind of like slope. So the big long formula for average rate of change is equal to f of b minus f of a over b minus a. So this looks really similar to the slope formula that you should be used to. So on the top, we have a difference of y values, and on the bottom, we have a difference of x values. But since we've already found the net change, we actually have a slightly easier way of doing this. So we don't have to do f of b minus f of a again. We can just plug in our net change. So this is the same as the net change over b minus a. The net change we had was 12, and then b was 0, and a was negative 2. So we have 0 minus negative 2, which turns into 12 over positive 2, which is just 6. So our average rate of change for this function between 0 and negative 2 is 6. For our next problem, we're given some functions, and we want to describe how the graph of each function can be obtained from the graph of f. So f is just any old function, and basically what we're going to do is we're going to apply some transformations to it, and that's the function we've been given. So our job is to determine what those transformations were. So for our first function, we have 1/3 times f of x minus 8 plus 4. So the key here is to break up what each of these numbers mean in this function. So first, we might look at the negative 8. So when we have a negative 8 inside of the parentheses of our function, what that means is we want to shift it either left or right. And the way we do that, the way we figure out which one it is we look at the sign. So since we have a negative sign, horizontal transformations usually do the opposite of what you think. So a negative sign actually means right 8 instead of left. So right away, let me go to my answer choices and see which ones I can eliminate. So anything that says 8 units to the left, I can strike out right away. So I can strike out this one as well as this one. So next, let's look at the 1/3. So notice that the 1/3 is outside of the function, so it's being multiplied by f. So this is going to tell us to shrink vertically. So right here, I can cross out this first answer because we're not stretching vertically, we're shrinking vertically. And so finally, I need to decide what this positive 4 is going to do to my function. So the positive 4 outside is a vertical shift, and vertical transformations do exactly what you think they will, not like horizontal where it's backwards. So a positive 4 means we're going to go up 4. So our correct answer is the second choice. So for the second function, we're going to do the exact same process. So we have 4 times f of x plus 1 plus 5. So first, let's look at the horizontal shift. So we have a positive 1 right here, which tells us to shift left 1 unit. So any of these answer choices that doesn't say 1 unit to the left, we can strike out immediately. So that's the first one and the fourth one. Now let's look at the vertical shrink or stretch. So a 4 on the outside of f, so unlike the fraction which told us to shrink, a number like 4 is going to tell us to stretch. So any of the answer choices that say shrink, we can cross out right away. So we're left with 2 choices. So what we need to decide is whether the positive 5 tells us to shift up or shift down. And from the previous problem, we know that this tells us to shift up. So the answer that we want is the third one. In this next problem, we're given a function and we're given a bunch of choices of graphs, and we want to match the graph to the function. So don't pay attention to this dot in the bubble right here. That was my mistake when I was making the PDF. That's not necessarily the correct answer. So our function is y equals negative absolute value of x. So just as a little reminder, the graph of the absolute value of x looks like this. So we have our 4 quadrants, and we have a line going like this and a line going like this. So that is y equals absolute value of x. If we want to change it to the negative of the absolute value of x, this negative sign tells us to reflect over the x-axis. So we're looking for a picture that looks exactly like the one I drew on the right, except the graph is basically turned upside down. It's not moved anywhere. All it's done is reflected over that x-axis. So the graph that looks like that is this one right here. So notice that it still has the point at 0, 0, and all that we've done is taken the original graph and just flipped it over the x-axis. So that is our graph. In problem 4, we have a function f is given, and we're also going to be given some transformations that have been applied to the function, and our job is to get the equation of the final transformed graph. So instead of being given the equation and determining the transformations, we're now given the transformations and have to determine the equation. So let's translate each of these transformations into equations. So first, I see shift 8 units to the left. So what does that tell me? Well, I know that shifting to the left is going to affect the inside of the function, and by that I mean like if we have a grouping symbol like a parentheses or an absolute value sign or a square root, this is going to affect whatever's inside of that. So if I'm shifting 8 units to the left, I'm actually going to add 8 to x. So the way we translate this into an equation is we're going to put plus 8 after the x. The other transformation I have is to shift downward 4 units. So if you recall from the previous problems, we said a downward shift is going to be outside of our grouping symbol, whether that's a square root or a parentheses or an absolute value sign, it's going to be outside of those symbols. So if we're shifting downward, we're going to have minus 4 outside of absolute value of x. Okay, so now I've translated both of my transformations into what I'm going to do to the equation, so let's just write the final equation. So my final equation, I guess I'll still call it f of x, really doesn't matter. So we said we were going to add 8 to the inside and subtract 4 on the outside. So our final equation looks like this. We have f of x is equal to the absolute value of x plus 8 minus 4. In this next problem, we're going to review addition, subtraction, multiplication, and division of functions. So we're given the two functions f of x is equal to x squared plus 8x, and g of x is equal to 5x squared minus 1. So we're going to do all 4 of the function operations and get 4 new functions, and then we also want to find the domain of each of the functions. So the first one we're going to do is f plus g of x. So if you recall, when we do function operations, it's really exactly what you think you should do. So if it tells you to add f and g, that's exactly what we want to do. So we're going to write the function f, and we're going to add to it the function g. So we're just going to add everything together just like that. And what I want to do now is just combine any like terms that I may have. So x squared plus 5x squared gives us 6x squared plus 8x minus 1. So f plus g of x is the 6x squared plus 8x minus 1. For f minus g of x, we're going to do the same thing, except the second function is going to get a negative sign outside. So we have x squared plus 8x minus, and then I'm going to open a parentheses and write g. So we have 5x squared minus 1. And the reason I'm doing this is because if you don't write the parentheses, then you may only put the negative sign on the 5x squared. So if you write the parentheses, it helps to remind you to take this negative, which is what we're going to do next, and distribute it across the parentheses. So if we start simplifying, we have x squared plus 8x minus 5x squared plus 1. And if we simplify this a little bit further, we can combine the x squared terms and get negative 4x squared plus 8x plus 1. So that's f minus g of x. For f times g, again, we're going to do exactly what it basically tells us to do. We're going to take f, which is x squared plus 8x, and we're going to multiply it by 5x squared minus 1. So when you have two polynomials being multiplied together, remember that you have to FOIL these. So you can't just like multiply the first two, multiply the second two, and then say, oh, I'm done. No, we got to make sure we do every single one with every single other one. So first, we do x squared times 5x squared, which is 5x to the 4th. Next, I can do 8x times 5x squared, which gives me 40 times x cubed. Then I have x squared times negative 1, which is negative x squared. And finally, I have 8x times negative 1, which is negative 8x. So that is f times g. There's nothing else to simplify here because all the variables are different. And then our final function we need to find is f over g of x. And just like with the other three, you basically do exactly what you think you would do. So if we want to divide f by g, we're just going to write the function f on the top, draw a big fraction bar, and write the function g on the bottom. So we get x squared plus 8x divided by 5x squared minus 1. So those are our 4 functions. Now we need to find the domains. So the nice thing about these is addition, subtraction, and multiplication all have the exact same domains. And the way we do this is first we want to think about the domains of each of our individual functions. So first, f of x is x squared plus 8x. So that tells us, since we have an x squared, and that's the biggest power in our polynomial, we know that that graph is going to look like a parabola. And parabolas have domains of negative infinity to infinity. So f, the domain, is just all real numbers. For g, we also have a parabola, or a quadratic function, because our biggest power of x is 2. So once again, the domain of this one is going to be negative infinity to positive infinity, or all real numbers. So the way we get the domains of the added, subtracted, multiplied functions is we're going to think about these two domains and where they overlap. Well, since these two domains are the same, they overlap everywhere. So the domain of the first three functions is just going to be all real numbers. So we have negative infinity to positive infinity. So instead of writing it 3 times, I just grouped them together and said all of their domains are the same and they're all real numbers. Now, when you get to division, it's a little bit different. So if you remember with domains, we can have two big problems. One, we could have fractions and the denominator equals 0, or we could have square roots and have a negative number under the square root. Here, our problem is the fraction. So it would have the same domain as the other three, but we also have to exclude those numbers where the denominator equals 0. So to see where the denominator equals 0, we just take 5x squared minus 1 and set it equal to 0 and solve for x. So 5x squared equals positive 1, x squared equals 1 over 5, and so x is just plus or minus the square root of 1/5. And if you wanted to simplify this a little further, you could say this is plus or minus 1 over the square root of 5. So now that we found the places where the denominator is 0, let's translate this into an interval. So we're going to start with the interval negative infinity to infinity, but we're going to cut out the 2 points negative 1 over the square root of 5 and positive 1 over the square root of 5. So let's start with negative infinity. So our domain should include every number from negative infinity up to negative 1 over the square root of 5. And then we want to skip over that. So our next interval is going to start at negative 1 over the square root of 5 and go up to positive 1 over the square root of 5. And then we're going to have one more interval because we want to skip over that 1 over the square root of 5. So our final interval is going to be 1 over the square root of 5 up to infinity. So as you can see, we just took the interval negative infinity to infinity, and we took out the 2 points that don't work for our function. So this chain of 3 intervals is your domain for f divided by g, whereas this one up here is your domain for the other 3. Next, we're going to review a bit of function composition. So we're given the functions f of x is equal to 3x minus 5 and g of x is equal to 4 minus x squared, and we want to evaluate the following 2 expressions. The first one, we're given f of x. So another way to write this is f of x. And I like to write it this way because it reminds me what I want to plug into what. So this is telling me I want to take the function f and plug it in to the function f everywhere I see an x. So we're going to have 3, but in the place of x, I'm just going to put the entire function f. So I'll have 3 times 3x minus 5 minus 5. And if I simplify this, I can distribute the 3, which is 9x minus 15 minus 5, and then combining like terms gives me 9x minus 20. So 9x minus 20 is f of x. Our next function we want to find is g of x. So just like we plugged f into f, this time we're going to plug g into g. So again, if it helps you to remember what to do, you can rewrite it like this, g with g plugged in the place of x. So we're going to have 4 minus, but in the place of x, we're just going to write the function g again. So we have 4 minus x squared in the parentheses, and don't forget that extra square outside because that was in the original function. Okay, so now all we have to do is just FOIL things out and simplify. So we have 4 minus, and if we square out 4 minus x squared, we'll have 16 minus 8x squared plus x to the 4th. So just be careful. Remember that when we square something in parentheses, we have to FOIL out 2 identical copies of the thing in the parentheses. So this is what we get if we do that. Next, we can distribute the negative to get negative 16 plus 8x squared minus x to the 4th. And then we can combine like terms. So we have negative 12 plus 8x squared minus x to the 4th. So that is the function g of x. So we're going to continue with this idea of function composition, except this time when we find all of the different composed functions, we're also going to find their domains. So these are not as nice as the ones that we did before with addition, subtraction, multiplication, and division. Each one of these composite functions is going to have a different domain, for the most part. Sometimes you might be given really nice functions, but I can tell you right away that f and g in this problem are not going to be super friendly. So first we might start by discussing the domains of f and g individually. So f is a fraction, and we know that a problem with fractions and domains is we don't want the denominator to equal 0. And here our denominator is x plus 3, so the number that makes the denominator 0 is -3. So the one number that we can't have from f is -3. So instead of writing out the big long intervals, I'm just going to say x is not -3. On the other hand, g of x is just 5x minus 3, which is a linear equation. So remember, those are things that look like y equals mx plus b. So we can see how that fits that pattern. And lines have all numbers in their domain. So g of x's domain is all real numbers. So now that we've found the individual domains, let's go about finding the composite functions. So first we need to find f of g of x, which is f with g plugged in. So we're going to start with a giant fraction, and in the place of x, we're going to put 5x minus 3. So we have 5x minus 3 divided by 5x minus 3 plus 3. Okay, so it's not necessary to simplify these all the way. Some of your answer choices on your final might be simplified, but for the purposes of finding domains, it's much easier to keep it in this form. So we're going to leave it like this. Okay, so the way to think about domains is first we want to think about the function that we plugged in. So the function we plugged in here was g, and g has a domain of all real numbers. So that's sort of where you start with thinking about your domain. And then you say, okay, once I plug this function into the other function, does my domain get restricted any further? So in this case, we're starting with a domain that's not restricted, and maybe the fact that we plugged it into this fraction is going to make us have to exclude some numbers. It's a fraction, so you should assume we'll have to exclude some other numbers. So to figure this out, we need to see where this denominator is going to equal 0. So for the domain, we need to see where 5x minus 3 plus 3 is equal to 0. So this is the same as seeing where 5x is equal to 0, and that's when x is 0. So our domain for f of g of x is going to be -infinity to 0, together with 0 to infinity. So just to reiterate, we started with the domain of the thing we plugged in, and then we saw if we could restrict that any further. So this one might be a little hard to see why that process is the way to go about this, but I think in the next one it might be a little more obvious, or maybe the third one. We'll see. So next we want to find g of f of x. So this time we want to plug the function f into the function g. So we're going to have 5 with a parentheses minus 3. So that parentheses is representing our x, and in the place of x we want to write the function f. So that's x over x plus 3. So let's see. So we want to think about the function we plug in first. So x over x plus 3, we know the only number we can't have in our domain is -3. So then we want to ask ourselves, when we plug that into the linear equation, does that restrict our domain further? And here the answer is no, because the domain was -infinity to infinity. So the domain of g of f of x is just going to be the same as the domain of f. So the way we write x not equal to -3 as an interval is we say -infinity to -3 together with -3 to infinity. So the next one we want to find is f of x. And so I think this is where you're really going to see where the process I'm explaining for finding the domains is going to come in handy. So this time we want to take the function f and plug it into itself. So our backbone of this equation is going to be a giant fraction bar. And in the place of the x on top, we're just going to write x over x plus 3. And on the bottom, we're going to have x over x plus 3 plus 3. And so now you're really glad that I told you not to simplify, because this one would be a nightmare. So let's find the domain. Okay, so our domain of f does not include -3. So the first thing I'm thinking about is this little guy right here. So for each of those fractions, I know that -3 is going to be a problem. So I know right away I can't include that in my domain. However, we also have this bigger denominator to worry about. So because I plugged that fraction into a fraction, I also have to figure out where that big denominator is 0. So I'm going to take x over x plus 3 and set it equal to 0, and that's going to be another number that I have to exclude from my domain. So I can subtract over the 3, so we have x over x plus 3 equals -3. I can multiply the x plus 3 to the other side, so we have x is equal to -3 times x plus 3. Distributing, I get x is equal to -3x minus 9. Excuse me there. And then I can add over the 3x, so I get 4x is equal to -9, and so x is equal to -9 over 4, which for the purposes of writing our interval, let me think, that's -2.25. So the only reason I'm saying this is because when we write our interval, we want to make sure all of our numbers are in the correct numerical order. And sometimes it's easier to tell that when we have decimals rather than fractions. But we're going to write the fractions in our interval. So let's go about writing our final interval. So we're going to start by going from -∞ to -3. Because -3 we're going to hit before we hit -2.25. My second interval is going to be -3 to -9 over 4. My third interval is going to be -9 over 4 to infinity. So notice what we did here. We started with -∞ to infinity. We took out -3 and we took out -9 over 4. So this whole expression here is your entire domain. So I know this is getting a little repetitive, but we have one more. We have g of x. So this time we want to plug g into itself, and this one's going to be a lot nicer, I promise. So we have 5 times 5x minus 3. So notice we just took 5x minus 3, plugged it in for x in 5x minus 3. So here, first think about the 5x minus 3. It's a line, so we said its domain was all real numbers. If we plug that into the same equation, we're not restricting the domain any further because the line had no problems to begin with. So the domain of g is just going to stay all real numbers. See, so I told you that one was nicer. So that concludes our review of composite functions. For this next problem, we're going to find the inverse function of f. So you might recall that in class we talked about that a function can only have an inverse in certain cases when it's what we call one-to-one. But here we don't have to worry about that because we're going to assume that any function they give us already has an inverse, and our job is just to find it. So we're given the function f of x is equal to 1 over x plus 6. And so if you remember, the first step to finding an inverse is we just rewrite our function with y in the place of f of x. So we're going to rewrite this as y is equal to 1 over x plus 6. The next thing I want to do is swap the places of x and y. So I'm going to write x is equal to 1 over y plus 6. And now my job is to solve for y again. So let's see what I can do. I can multiply y plus 6 to the other side. So I'll have x times y plus 6 is equal to 1. And now you might be tempted to distribute here, but I would caution you against that only because we're only focused on getting y by itself. And if we simply divide by x instead of distributing, we're going to be closer to doing that. So you could distribute, maybe move a few things around, but it's just going to take you a lot longer. So let's divide by x. So we have y plus 6 is equal to 1 over x. And then finally, I can just subtract the 6. So we have y is equal to 1 over x minus 6. And my final step is just to replace the y with our f inverse notation, which is f with that little -1 superscript. So we have f inverse of x is 1 over x minus 6. So this is your inverse of f. All right, for our next problem, we're going to drift away from functions a little bit, or functions in general, and we're going to go to logarithms and exponential functions. So in question number 9, we want to solve the logarithmic equation for x. So this is going to require you to remember some of your logarithm rules, and for a summary of those, you can see the other resources I've posted for you to review. But for now, we're just going to assume that you know them, and I'm going to go through the problem. So we have the log of x plus the log of x minus 48 is equal to 2. So right away, what I notice about this problem is we have two logarithms added together. So when you have two logarithms added together, you can combine them into a single logarithm with the insides multiplied together. So we can rewrite this as the log of x times x minus 48 is equal to 2. So notice I took the sum of logs and I combined it into the log of a product. So now what I can do is I can take this logarithm, so I have a single logarithm equal to a number, I can switch its form to an exponential. So it's been a while since we've done this, but basically a logarithm is always an exponent, and when a logarithm doesn't have a base specified as a little number subscript, we assume the base to be 10 unless you have ln, in which case the base is e. So we're going to have 10 to the second power is equal to x times x minus 48. And now we just solve this like any other equation. So 10 squared is 100. And if I distribute the x, I'll get x squared minus 48x. So my equation just becomes 0 is equal to x squared minus 48x minus 100. So now I want to think of two numbers that multiply to give me negative 100 but add to give me 48. And 100 has quite a few factors, but I noticed that 50 and 2 should work. So I can factor this into x minus 50 times x plus 2. And so that means that x is either going to be positive 50 or negative 2. Okay, so remember the tricky thing about logarithmic equations is that just because you get an answer, it doesn't mean that those answers are actually correct. So we have an extra step at the end. We have to check that our answers don't make x or x minus 48 turn into a negative number. Well, right away I see a problem with negative 2, so let me just write this so that you remember to check your answers. But anyway, so right away, negative 2 gives me a problem with x, because if I plug negative 2 in for x, well, that's going to be negative, because negative 2 is negative. So negative 2 does not work. And you could see this again by doing negative 2 minus 48. Well, that gives me negative 50, which is again negative, so that's not good. We don't want that as an answer. And so my only answer then is x is equal to 50. And you could check 50 with both of those and determine that it keeps the inside of the logarithm positive, and so 50 is an answer that is okay. All right, just a couple more questions to go. So this next one, we're going to review some compound interest. So a woman invests $6,100 in an account that pays 6% interest per year, compounded continuously. So if you remember, when you do these interest problems, you have two different formulas you need to use. One of them is if it specifies how many times it's compounded per year. So like if you have a keyword like annually or semi-annually or quarterly or monthly or daily, you're going to use the longer of the two equations. But here we have a continuous compounding, so we're going to use the equation A is equal to P times E raised to the R times T. So that is the continuous compound interest equation. And now we just need to figure out what all of our variables are. So we're investing $6,100, so P is 6,100. R is going to be our percent, but we want to write it as a decimal, so 6% as a decimal is 0.06. And part A tells us what is the amount after 3 years. So 3 is going to be T. So now all we have to do is plug in all of our variables. So P is 6,100. E is a number. That's a special button on your calculator. And that's going to be raised to the 0.06 times 3. So now all that's left to do is just plug this into the calculator, and you should get $7,303.03. So pay attention to the rounding directions. It says round to the nearest cent, so we want to go to 2 decimal places. Okay, our next one is how long will it take for the amount to be $11,000? So this time, we're not solving for A, we want A to be 11,000, and we're looking for the time. So how long tells us that we don't know how much time has passed. So let's again start with our formula. A equals P times E to the RT, and let's plug in what we know. So A is 11,000, P is 6,100, E to the 0.06, and T is going to be our variable. So T is in the exponent, so this tells us at some point we're going to have to use logarithms, but before we can do that, we have to get that exponential part, which is e to the exponent by itself. So the way we do that is we divide by 6,100, and don't actually get a decimal approximation for this. Leave it exact until the very end because it might throw your answer off. So 11,000 over 6,100 is equal to e to the 0.06 times t. And now that we have e isolated, we can take the natural logarithm of both sides. So we have the ln of 11,000 over 6,100 is equal to the ln of e to the 0.06 times t. The reason we use a natural log is because what it does is it cancels with the e and just leaves us with ln of 11,000 over 6,100 is equal to 0.06 times t. So the last thing we need to do to get t by itself is just divide by 0.06. So now that I have this entire expression equal to t, that's when I want to plug it into my calculator, and if you do that, you should get 9.83 years. So I wanted to round to 2 decimal places, so again, just pay attention to the rounding directions. Alright, so we're to our last problem in this video, and in this problem we're going to review the section that had to do with relative growth rate, doubling time, and half-life or radioactive decay problems. So this was that section in chapter 2, I think, or no, chapter 4, where, the whole section was word problems, and you had to decide which word problem fit with which equation. So in this one, we have radium-221 has a half-life of 30 seconds. How long will it take for 89% of the sample to decay? Round your answer to the nearest whole number. So right away, we're talking about an element with a half-life. So I'm going to jump to the radioactive decay equation. So if you recall, it's going to take me a second to write out radioactive decay. If you recall, the radioactive decay equation is m of T is equal to m sub 0 times 2 to the negative T over H. So m sub 0 is your initial mass of your element. The 2 is because we're talking about half-lives, so that has to do with 2. T is time again, and H is the half-life. So it's important to remember that whatever unit your half-life is given to you in, your time is going to follow the same unit, okay? So let's plug in what we know. So we know that we don't know T. We're looking for T. The half-life is 30 seconds, so I'm going to write 30 in the place of H. And we don't have an initial mass, but we're given a percentage of what has decayed. So when you're given a percentage of an element that has decayed, always assume that your initial mass is 100. And the reason we do this is because percentages and 100 go very well together. And so if 89% of 100 has decayed, it means 11% is left. So m of T, we can say, is 11. So m of T is whatever's left, okay? Not what has decayed, what is left. And that's important to remember because people get it confused all the time. So with everything plugged in, our formula becomes 11 is equal to 100 times 2 to the negative T over 30. So we want to solve for T. So the first thing we can do is divide by 100. So we get 0.11 is equal to 2 to the negative T over 30. So just like in the compound interest problem, we want to take the ln of both sides. So we'll have the ln of 0.11 is equal to the ln of 2 to the negative T over 30. So unfortunately, the ln doesn't cancel with anything this time because we have 2 instead of e. However, taking the ln of the right side allows us to take that thing in the exponent and move it out to the front. So we get ln of 0.11 is equal to negative T over 30 times ln of 2. So even though we don't get to cancel stuff out, it still helps us a little bit. So now I want to continue to get T by itself, so I can divide by ln of 2. So I get ln of 0.11 over ln of 2 is equal to negative T over 30. So I see the last thing I need to do is just multiply the other side by negative 30. So I'll have T is equal to negative 30 ln of 0.11 over ln of 2. So now that I have T isolated, I can take this entire expression here, put it in the calculator, and I should get roughly 96. And that unit is going to be seconds because our half-life was in seconds. So our final answer is 96 seconds. So that concludes this video on chapters 2 and 4. And I want to wish you the best of luck studying for your final.